Okay. So let's continue our discussion. Okay. So now you guys understand the definition of LP, UP, and CP. Okay. So, okay, let's have a look at this handled event point algorithm. Okay. So we know like the endpoints are already inserted into the our priority queue, right? So we will pop or we will get the event point with the minimum y coordinate value, okay, and then okay, so okay that UP be the set of segments, blah blah blah. So this is the UP is very easy to find, okay, because the segments are stored with the event point P. Okay, when we put the event point in the priority queue, okay, in the queue, okay, in this data structure queue, we will also associate this point with the segment that provide this event point. Okay, so that is why, okay, when you it's easy to find the set of UP, okay, because when you if an event point happen to be the upper end point of some segments, okay, you can easily obtain those segments from the top of the event queue. Anyway, okay. So for horizontal segments, the upper endpoint is by definition the left endpoint. Okay, so you can ignore this at this moment. Okay, we will talk about this degenerate case later. Okay, so find all segments stored in tree. Okay, in T. What is the segment? Where are the segments stored in the tree? Okay, those segments are what we call active segments, right? So they are adjacent. They are adjacent to in tree. Okay, so in the T. So those segments, okay, must be so if an event point, okay, let me show you. Okay, so you can see. Okay, if you are right above this point, you can obviously see that, okay, when this event point is considered, okay, in the active status tree, okay, of course all these seven segments are active, but you can see that, okay, no matter let's say, okay, well, actually, these segments, okay, the S5, S4, S1, S3, as well as S2, okay, they are, I mean, well, but probably not S2 because S2 are, I mean, well, S2 will be the top, the UP anyway, okay. So the other segments are neighboring to each other. So it will be easy to find out the CP and the LP. Okay, it's easy to find out CP. So if LP and the UP and the CP, the union contain more than one segment. Okay, if it contains one segment, that means it must be the endpoint. Okay, one endpoint of one of the segments. Then it's not considered as an intersection, right? I mean, you consider a point as an intersection only when this point is contributed by more than one segment from LP, UP, and the CP, right? So if the union of these three sets contain more than one segment, then you are going to report P as intersection together with all the segments, okay, that contain this point, okay. So in other words, okay, sorry. So when you have this point, okay, when you see this point, you are going to report, S1, S2, S3, S4, and S5. Okay, some of them are LP, some of them are UP, some of them are CP, but they will all be reported. Okay, they will all be reported. So the following action is very interesting. Okay, because we have to maintain the neighboring status in the tree, right? We have to maintain this neighboring status in the tree. But when you go past an intersection, you can imagine. Okay, for example, let's say here, here. Okay, when you go past the intersection, original when you are here, these two are neighbor, these two are neighbor, these two are neighbor. But when you go past the intersection, the neighboring status will change, right? The neighboring status will change. You see now these two are neighboring to each other. These two are still neighbor to each other, but these two become neighbor to each other, and these two will no longer these two and these two will no longer be neighbor to each other, right? Even though they are still, all these four segments are still active, right? So it's kind of complicated to maintain this order, right? What is the easiest way to deal with that? Okay, the easy way to deal with that is, well, you just delete these two segments from the tree, and then, okay, reinsert these two segments to the tree, but now using the right order. Because when you insert the segment into the tree, okay, you can specify their neighboring, situation, right? So now, okay, you delete them, and then reinsert them. Then the binary search tree will automatically maintain those information for you. Okay, so the concept here is you try to delete them, and then add the so here, okay. So you see, we delete the LP and the CP. For those segments, use P as a lower endpoint. We no longer need to insert them, right? When we go past P, those segments will be inactive anyway, right? So we no longer need to insert those segments. Okay, but for CP, we need to insert them in the right order. So what happens? We need to insert UP and CP into the T, this tree, the binary search tree, okay, so that they will maintain the right neighboring information. Okay, I believe one student asked me about 3 lines intersecting at one point. Okay, this can handle not only all the cases, including the 3 point intersecting at one point. Okay. So this deleting and reinserting CP will help to correct their order. Okay, so this is very important. Okay, otherwise it looks strange to delete the CP, the segments in CP, and reinserting them, right? But it makes sense when we try to maintain their order. Okay. So then, okay, there are some other cases to consider. If UP and the CP intersection, the union is empty, okay, that means P is not upper endpoint or the content in any segment, okay, then you need to find like it must be like two we need to find the intersection, okay. So let SL SR be the left and right neighbor of P in the tree. Then we will try to find the new event, okay, of SL SR. SL SR, remember, SL and SR are segments, okay, and the P, okay. So what is find new event? Basically, like remember I told you we need to consider the possibility of the neighboring segments that may create the next event point, right? Before, the next, I shouldn't say next event, the next intersection before the next event. Okay, so for example, I told you guys like, I already erased that, okay? So for example, like this, okay? Before this event point, okay, there will be an intersection here, right? So we consider these two, the neighboring segments, to see like if we need to, if there's any event point that may happen before the next one. So this one we'll find this one, and we'll find this one, and then we'll insert. Okay, we'll insert that one into the event queue. Okay, which will be handled in the find new event subroutine. Okay, there are three different cases. Because because one of them is like when you are the leftmost one, the rightmost one. The third case is like if you have like a segment like left segment and the right segment. So we write them like in the separate cases. This is if there are left segment and right segment. This is if we only have right segment, and this is if we have only left segment. Okay, just that's it. Okay. So let's use this as an example. Okay, so before we reach this point, okay, so the binary search tree structure is like this, and you can see that. Okay, let me make it clear. Okay, this is binary search tree. So if you write your program, your result may be a little bit different from this one, but the left and the right relationship should maintain. Or it should be like that. Should be just like this. Okay, you can see S7 is on the left side of S5, which is on the left side of S4, and then S1, and then S3 and S8. Okay, so you can see S7, S5, S4, S1, and S3 and S8. Okay, it represents the left and the right relationship of this of the segment, of the active segments. Okay, and when you are at the point P, remember we will delete the LP and the CP, right? So what are the LP and CP? We talked about that already, right? The LP will be S5, okay, and S4. right? S5 and S4 are LP, right? And S1 and S3 are CP, right? So we will delete S5, S4, S1, S3 from this tree. Okay? We'll delete all these 4 nodes. Okay? Most likely we'll end up having, well, just 2 nodes, something like, it's, the only thing left will be this is S7 and S8. Okay, we only have these 2 segments left. Okay, and then we will insert, after that, we will insert the CP and UP into this data structure. So, so in other words, we'll insert S3, S2, and S1. S3 and S1 as CP, S2 as UP, right? So we'll insert them. So it will become something like this. Again, depending on your implementation of binary search tree, your result may be slightly different from this one. But the order, the left and the right relationship should be like this. Okay. Get it? Okay. Good. So, as for the find new event, basically, like when you have these 2 segments, we will have to check if there's an intersection between these 2 segments with inside the segment, not outside of segment. Okay, I mean the reason to provide a P is because we want to make sure it is it is to the right of the current event point P. So you may ask like why do we do that? Okay, this is for degenerate case. Okay. So now it's and then when we find it, if we find the intersection, we'll insert the intersection point to the event queue, and then let the main algorithm to handle it, because it's going to find the next event point from the queue anyway, and deal with that. Okay, so now it's probably a good time to talk about the degenerate cases. There are 2 things that we need to consider. The first thing is, how about the situation that the segment is horizontal? Okay, when the segment is horizontal, we are going to consider like the 2 ends. So or put it in a more general cases. Okay, if you have more than one event point, if you have more than one event point that have the same y coordinate value, which one should we handle first? We will handle the event points. Okay, if they have the same y coordinate value, we'll handle them based on their x coordinate value, from left to right. Okay, so this will also help to deal with the horizontal line segment, because in that case, for the horizontal line segment, the endpoint, one of the endpoint will have a smaller x coordinate value, right? Okay, so it will be considered first. Okay, or put it another way. Okay, the endpoint. Okay, if a segment is horizontal, if segment is horizontal. And then this one is considered the UP. This one will be considered as LP. Say if that segment is horizontal. Okay, then what happens is that, okay, because they have the same y coordinate value, right? So when you deal with this point, okay, when you the first point that gets dealt with is this UP, okay, and then this will be inserted and then be considered if there's any intersection with other segments. Okay, but because you know, if there's any event point that happen in between, let's say there's an intersection here, then this point will be found out because after we insert this segment, okay, after this UP, okay, after we deal with the UP, we will find out this point, and then this point will be inserted into priority queue, into the event queue. And remember, I told you the event queue will handle the event point, like you know, according to y coordinate. But if this, I mean, because this one we already deal with this one, right? But if this one is inserted, it will have a higher priority than this one, right? Right? So we are going. So this segment is going to be considered as like if we call this Q, okay, let's call it Q because I shouldn't use P here because, well, this is P, this is a different point. I should use P. This is R, okay, and this is if this is Q, so this is CQ. So we are going to deal with P first, and then Q, and then R. Okay? We are going to deal with them, something like that. And this segment will be handled correctly without any problem. So that's the first degenerate cases. The second degenerate case is like, okay, if you have like a, well, let's say these two intersection. My drawing is very poor actually. Okay. These two intersections happen at the same x coordinate value, but they are provided by two different two different set of segments. Okay, same thing here. Okay, we are going to deal with this point first, and then this point. But this is the exact case why we need to provide, okay, the P here, because you can see, okay, let's say if this is a P, okay, see, we may need to find, okay, the intersection, you know, find or on it or to the right of the current event point P, which is this point. This point. Okay, and then we will insert that into priority queue to deal with that. Okay. So both of these degenerate cases will be considered. Okay. So then, okay, we need to consider the complexity, the time complexity of this algorithm. How quick, how efficient is this algorithm, right? A lot of time, like in computational geometry, it appears that it is actually easier to talk about the idea than to talk about like the mathematical derivation of the time complexity. Okay, it is actually, I mean, it looks complicated, but actually this is perhaps one of the most the simplest one. Okay, because later on you are going to see like some more complicated derivations, especially in when we talk about like random algorithms. Okay, randomized algorithm. Okay, randomized algorithm. First, okay, so our algorithm take big O n log n. Oh, sorry. N log n plus I log n. This is I. Okay, I log n. Okay, the n represent the number of line segments. I represent the number of intersections in S. And just want to remind you, okay? Remember, when we talk about this algorithm, I keep telling you guys, this is how we call output sensitive algorithm, right? Output sensitive algorithm. So when you have an output sensitive algorithm, the time complexity should be have something. The time complexity should have something to do with the size of your output. Okay, so you can see that. Okay, because I mean you see I log in here. I mean the I is the number of intersections in S, which happens to be the size of the output as well, right? Okay, and that's the first thing. The second thing, remember I told you, for output sensitive algorithm, in the worst case scenario, its performance is actually not necessarily better than the intuitive algorithm that we talked about. Remember the n squared algorithm. Remember? Okay, let's look at the case. Okay, before we prove that. Okay, anyway. Okay, we'll prove that shortly. Okay, so this big O n log n plus I log n. So assuming the intersection happen to be quadratic, that's the worst case scenario, right? So the time complexity will be what? Will be dominated by this term, right? It'll be n squared log n, right? N squared log n, which actually is worse than the intuitive algorithm that we discussed at the first place, right? Okay, so I just want you guys to be aware, okay? The output sensitive algorithm is good when the output size, in this case, when the number of intersections is not too many. But if you know for this particular application, you are going to end up having a lot of intersection. If that's something you observed, then you shouldn't use this algorithm. Okay, because using this algorithm actually doesn't provide any good anyway. It's actually, in terms of time complexity, it's actually worse than the intuitive one, right? Which this is very common in the output sensitive algorithm. Okay, so just want you guys to be aware of that. Okay, so now let's prove that this is the complexity of the algorithm. Okay, so we know like each operation on our status tree take big O log n y because there are only insertion, deletion. Okay, insertion, deletion. I mean of this status tree, right? Status Q tree. Okay, we know like the insertion or deletion of the binary search tree takes log n, okay, assuming it is balanced one, okay, and the number of operation is linear to, okay, when you deal with 1 point, okay, the number of operation will be linear to the LP union UP union CP, the cardinality of this. Let's call that NP, okay? Let's call that NP. This is right? Because in our previous discussion, okay, for example, like all these operations, you can see that okay, it has something to do with cardinality of LP, CP, UP, right? So I hope like this is not going to be very difficult to observe for you guys, okay? So an event point P is a vertex of the graph, and the NP is bounded by the degree of the vertex, okay? So so if we denote the sum, so here, okay, I just want you to be aware, okay, even though we are dealing with some line segments, okay, we could consider those line segments as a planar graph, right? As a planar graph. Okay, of course, well, it's just like this planar graph is composed of some line segments. That's it, right? So if, in that case, the event point P is a vertex of the graph, of this planar graph actually. Okay, and the NP is bounded by the degree of the vertex, okay, of this planar graph. Okay, try to consider that as a planar graph. Okay, and then if we denote the sum of all NP over all event point P by n, okay, then we are talking about the sum of all the degree, right? The sum of all the degree. Okay, then the running time of the algorithm is big O m log n. N, we just denote all this NP as n, right? Now, and then each operation takes log n amount of time, so it's big O m log n. This is, I hope this is not too difficult to observe. Okay, and then n is bounded by the sum of degree of all vertices of our graph. Okay, so for a graph, the sum of degree of all vertices of a graph obviously is bounded by 2 times number of edges, right? Because each edge can provide 2 endpoints, right? To the degree, right? Right? So this is the first equation. N is smaller or equal to 2ne. This is obvious, right? Right? Okay, where this ne represent the number of edges in this planar graph. Okay, number of edges in this planar graph. So for example, when we consider this as a planar graph, here we consider this case not to be only 7 edges. We consider this case to be 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 edges. Because now this one is one of the vertices. So this vertex will break S1 and S3 into 2 segments, each into 2 segments. Okay? So NE, you may ask, like, why NE is not N? Because NE and N are defined differently. Okay, NE and N are defined differently. Okay, so I want you guys to be aware of that. Okay, and we know number of vertices is going to be smaller or equal to 2n plus I. Why? Well, the NV is actually number of, it's going to be number of event points, right? NV is going to be number of event points anyway, right? So what are the event points? Well, the endpoints, okay, of all the segments is going to be 2n, and as well as all the intersection. So I, right? I is the number of intersections. So why do I say it's smaller or equal to? Because, well, those intersections could happen at endpoint, right? So when you say 2n plus I, it actually may be bigger than the event point set, right? Right? So far so good. Are you guys with me? I know, like for some students, when I talk about math, some students fall asleep or something. Yeah, it is. Trust me, this is one of the easiest equation derivation. If you have question, try to. You can tell me to stop. Okay, and explain it again. That's not an issue. Okay, so up to this point, any question? I hope by now you guys are with me. And we know every phase, you know phase, right? I hope like you get an idea of phase from discrete math course. Okay, by the way, I also teach discrete math. Last semester I taught like a planar graph. Well, so I did cover that, the phase concept. Okay, the phase, for example, like well, unfortunately, there's not much phase I can talk about. For example, okay, so this is a phase. This is a phase. This is a phase. We have three phases here. Okay, this one, two bounded one, and one unbounded phase. Okay. So we know each phase, it could be bounded or unbounded. Okay, of the graph is bounded by at least. Here, okay, sorry, I'm only referring to the bounded phases. I do not include the unbounded one. Okay, the bounded phase it must be bounded by at least 3 edges, right? At least 3 edges, because a phase could be surrounded by, for example, 4 or 5 segments, right? It doesn't have to be surrounded by 3 segments. For example, this phase is surrounded by 4 segments, or 4 edges. Let me not use a segment because this one is 4 edges, right? This phase is surrounded by 4 edges. This one is surrounded by 3 edges. But every bounded phase must be bounded by at least 3 edges, and an edge can bound at most 2 different phases. Right? Okay, so because of that, we have NF, number of phases, is going to be smaller or equal to the number of edges times 2 divided by 3. Okay, based on this observation. Okay? Because this is at least, at most, so we have small or equal in the middle. Okay? And then we have Euler's formula. Euler formula, you should have learned that from discrete math. Okay? If not, okay, it's the right time to pick it up. Okay, for any planar graph, okay, the number of vertices minus number of edges plus number of faces, okay, will be greater or equal to 2. You may argue, okay, come on, when I was taking discrete math, my teacher told me it's going to be equal to 2, not greater or equal to 2. Why there's an inequality there? It is because, okay, in the discrete math, when we talk about Euler's formula, normally the examples that we use are connected graph. If graph is connected, then for a planar connected graph, yeah, the equation, the equality holds. Okay, but if the graph is disconnected, then this result, okay, NV minus NE plus NF is going to be greater than 2. Okay, let me use the example. A very simple one. How many vertices do we have? 6, right? How many edges do we have? 6, right? So 6 minus 6 is what? 0. How many faces do we have? 1 unbounded one, 2 bounded ones, right? So the total will be, so 6 minus 6 plus 3 is going to be greater or equal to 2, right? Okay, because in discrete math, when we talk about Euler's formula, normally the graph is connected. But now, the graph is not necessarily connected. Actually, we try to treat the segments as graphs. So most likely, the graph is not connected anyway. Okay. So once we have that, okay, you can plug in, because we know NV is smaller or equal to 2n plus 1, right? So we can replace NV by 2n plus 1, as well as we can replace NF by 2NE divided by 3, okay? So we have this, right? And if you try to sort it out, because the only thing left, the only unknown that is left is NE, right? So you can, get this NE is smaller or equal to 6n plus 3i minus 6. Okay? So why is this important? Because we know, remember, n is bounded by two times of NE, right? So we know n is smaller or equal to 12n plus 6i minus 12, right? So this one, remember the running time of the algorithm is big O n log n, right? So it's going to be, it's going to be bounded by 12n plus 6i, this minus 12, we don't need to account for that. But it's going to be n log n plus I log n, right? It's linear to these two terms, obviously, right? So we have that. Any question? Yes.
To apply Euler's formula for all the algorithms.
For all the algorithms.
For all the algorithm analysis in the geometry computer.
You mean computational geometry?
The computational geometry. To apply Euler's
Yeah, you are going to see Euler formula, I mean, several times. Not necessarily all the time, but a lot of times, yes. Yes. So it is a good idea to remember Euler formula. But I don't want you to memorize that. I mean, in an exam, if I will ask you something to derive something out of the Euler formula, I will give you that. I don't like memorizing stuff. I have bad memory. Okay, I never memorize stuff. Okay, so anyway, so just want you guys to be to understand this derivation. It's actually very simple. Very, very simple. If you understand the planar graph, concept, this is relatively, I mean, very simple. Okay. Okay. So, 11 o'clock already. Okay. Let's take 10 minutes break. When we come back, we'll talk about subdivision. Okay. Sorry. 手没有。 Okay. My progress is slower than I expected. Okay. I'm supposed to finish this set of slides today. Okay. But it looks like I still have like 13 slides. Well, excluding the last one, I still have 12 slides. Well, anyway, let's try our best. Okay. So we finished the discussion of the line segment intersection. Okay. So now we are in the position to talk about the subdivision. Okay. So in the subdivision case, the first thing that we need to consider, okay, before we talk about the overlaying two subdivision, is how do we represent a subdivision? What data structure should we use, okay, for the subdivision? Remember, we are going to represent a map by a subdivision, right? So, because it's going to be a map, right? So the operations that we need to be able to accomplish include the following three, okay? We need to work around the boundary of a face, because a lot of time we need to find like a certain area, okay, which is bounded by a number of edges, okay? So we need to be able to work around the boundary of a face. And we also need to be able to access one face from an adjacent one, okay? So the face, I mean, some faces are separated by the edges, right? So we need to be able to, to visit another face from one face, from the edge that separates these two faces, of course, okay? And also, we need to be able to visit all the edges that around a vertex, okay? They are around the vertex. So these edges should be, what should I say, incident to this particular vertex. Okay, so we need to be able to do that. Okay, so how to do that? What data structure is appropriate for these purposes? Okay, so it turns out that, okay, I probably have to cut certain discussion, okay, because as I said, like it appeared that I spent too much time on the previous question. So so the doubly connected edge list is a well-known data structure that can achieve all these purposes. Okay, so what is a doubly connected edge list? Okay, this name looks scary, right? I mean, you have never, I believe by now you have never heard of any data structure that is consisted of 4 words, right? It's kind of scary. I mean, doubly connected edge list, right? But actually, it's probably easier than you may think once you understand it. Okay, this data structure is specially designed to for the subdivision. Okay, because subdivision, as I said earlier, it consists of vertices, faces, and edges, right? So it has 3 separated different set of records. Okay, the first one is the set records for the vertices. The second one is the records for the faces. The third one is the record for the edges, but we call them half edges. Why do we call them half edges? Because we are going to represent each edge by, in the map, we normally do not associate the direction to edge, right? But here, okay, because we want to be able to walk around the boundary of a face, so we need to kind of associate a certain direction to the edge. Okay, So an edge is now represented by two different half edges. Okay, one is going from one endpoint to the other. The other one is from is reverse. Okay, so let me first introduce a couple of notations. Okay, in a doubly connected edge list. Okay, say we have a subdivision like this. Okay, so vertex V. Okay, vertex record V. What does it store? Okay, it stores the coordinates of that vertex. Obviously, we need that, right? As well as a pointer. Okay, this pointer will point to incident edge V to an arbitrary half edge that has V as its origin. So it is. So for example, say this is a V. This is a V. Okay, and it's going to this record, the record for this vertex V, include the coordinate of this point as well as a pointer that point to one of the half edge that use this point as a origin. Okay, origin. I mean, for example, this E, E goes from this point to this one. So this E use this point as its origin. So you can have a pointer to point to this one. Of course, you will also have an edge to go from here to here, and have an edge to go from, I should say half edge to go from this point to this one. Okay, but that's fine. I mean, because we only need this pointer only need to go to point to one of the half edge that use this point as the origin. Okay, so you can use this half edge E. Okay, and the phase record F. Okay, so for example, this is a bounded phase, right? This is a bounded phase. So this phase record F store pointer outer component F and a list of inner components F. What is outer component? What is inner component? Okay, I will explain using an example. But for now, okay, let me just say like the outer component represent a list of edges that bounds this phase. Okay, and the inner components are the holes in this phase. A phase could have some holes, right? So, for example, like we could have like okay, something like this. Okay, so this phase F, this phase is bounded by this list of edges, and it has two holes, right? Two holes inside this in it. Okay, so that's why. Okay, for the boundary for the boundary, I mean, a phase can only have one boundary. Okay, so we have like an outer component. It's a singular form, right? But for the inner components, you could have many holes in a phase, right? Such as this case, we have two holes, right? Okay, but how do we represent this list of edges? We actually just use one edge. We just use one edge. Okay. Well, I will show you by example later, okay? As for half H what record, okay, E, okay, it stores the pointer that points to the origin E, so the origin of this half H, okay, of course this is a vertex, this is a vertex, okay, and it also has a pointer that point to another half H. We call that twin, okay? For example, if this is the E, then its twin is the opposite direction half H, okay? So if this is E, this is twin of E, okay? Okay, and then it will have pointer to point to incident face. So this is a pointer to point to face. Okay, but which face to point to? For edge, remember an edge separate at least. I mean, there will be two faces. I mean, at most two faces on either side, right? Okay, so which face it points to? Okay, this is not arbitrary one. Okay, it is if we are standing on the origin, facing the direction, the face that we I mean this pointer is going to point to is on your left hand side. So which means if this is the H, then its incident face will be this one, not this one. Okay, it's going to be this one because on the left hand side of this face. Okay, and the next E is like an H that like I mean for example, this is the next E. Is the next half H. Okay, next half H. Of course, a half H could have more than one possible next H. Okay, for example, you may have another branch, okay, to the top. So the next could be point to this one. It could be point to the upper one. Okay, but which one does it will use? It will use the next is going to be, you know, what should I say, like the one that has the same incident phase. Okay, not the top one, because the top one, if there's a top half H, you can see no matter how you draw it, okay, the incident phase is not going to be this one, right? Okay, to have the incident phase to be the same as this one, the next half H has to be this one, because on the left hand side it's going to be this one, and the previous half H is going to be this one. Same thing, okay, applied. I mean, it has to be with the same incident phase. Okay? So because we have this next and the previous, so you can see that we are able to work around the boundary of a phase. Right? Okay. And how do we access one phase from an adjacent one? Because okay, so this is the incident phase for E, right? So for so the phase that adjacent to this one, okay, the other side. How do we access that phase? Yes, the instant phase of the twin edge of E, right? Good. So actually, like we are able to also accomplish the second task. How about the third one? Visit all the edges around a vertex. How do we do that? Given a vertex, okay, we have arbitrary half edge that use V as its origin, right? So for example, say here. So this is one of the half edge, right? So if we want to access this one, how do we do that? We use the twin, the next of the twin. So we will get this one. And then we again use the next of the twin, we will get this one, right? So we are able to go to like different half edges that are originated from this pointer, so from this vertex, right? Okay. So any question here? So yes. Yes. Next what?
Is this necessary to use twin edge for over the
you don't have to. There are other. For example, you can use previous.
Okay.
Yeah, I mean, but similar. It will be similar. Yes. Yes. So any yes.
What is the third operation for?
The
To integrate over all the edges from a single vertex. What is this for?
we will get to that shortly. Yes. Yes. I mean, there are. I mean, when you do like a map, overlaying two map, you need that. Yeah. Hopefully, we have enough time to talk about that. Okay. Yeah. If you are going to ask me so many questions, come a little bit forward. Okay. Sit a little bit closer. Okay, so that I can hear you clearly. Okay. I'm not saying like I don't like you to come to the class. I mean, if you. I mean, I mean, there's a lot of space here. Yeah. Anyway, okay. So having discussed these ideas, let me use an example here. So this is one subdivision. Okay, you can see that the subdivision doesn't have to be a closed loop. Okay, it could be as free as like you have a, how should I say, like a pendant, okay, like here, okay, and we have of course a simple loop on the top, but a pendant at the bottom, right? That's fine, okay. So in this case, I mean, you can see that, okay, how many faces do we have? So first, let's look at the vertex. We have 1, 2, 3, 4. We have 4 vertexes, right? We have 4 vertexes. So we have 4 vertex records, okay? And their coordinates as well as their incident edges. Okay, you can see that, okay, you can check, I mean, each of the, for example, V2 is here, okay? So E42 is one of the incident edge, half edge that use V2 as the origin. It could be E42, it could be E12, right? Both of them are using V2 as its origin, right? Okay? So this is like, this represents the list of records for the vertex. And for the faces, okay, for the face, okay, you can see face F1, we have actually two faces here. F1, the unbounded face outside of this loop, and the bounded face F2 inside of this loop. Okay, so for the for F, okay, it's unbounded face, so it does not have outer component. Okay, this is unbounded, it doesn't have bounded. Okay, so it's near. Okay, the pointer that points to like the boundary is near. Okay, for the inner component, okay, so this F2 is somewhat to be considered as a whole for F1. Okay, so we are going to have a pointer that points to the half edge.